So, welcome back to microwave spectroscopy. In the previous video, we talked about the spectrum, what it looks like, and the specific selection rule, which led to absorption taking place at several values equivalent to 2b, 6b, where b is the rotational constant, and more importantly, that the peaks were at about 2b apart. And once we are able to calculate the peak, the separation of the lines, we can calculate the bond length by the relationship between the rotational constant and the moment of inertia. Now we are going to talk about the intensities of the spectral lines. The intensities of the spectral lines, as before, it's related to, it's talking about how high the lines are. The higher the lines, then the more intense the transition, which means there's a likelihood of transition going from one state to the other. According to a Boltzmann distribution, the population of states determines the intensity of spectral line. The population of states, or the relative population of states for states J, that's just any energy level, with respect to the ground state, is given by Gj over G naught, where Gj, or G generally, is the degeneracy of the state. When we talk about degeneracy, that's how many states exist with that particular energy J. So the population depends on the degeneracy of the state and the energy of the state, and also the temperature at which the transition is taking place. And we have our energy to be equal to J into J plus 1, that's the energy level. That energy, remember, is dependent on the moment of inertia. Now, the G naught for rotational state is 1, which can be obtained from here if you put the value of J equals 0 into that equation. That would be 2 times 0 plus 1, so that's 1. And the general expression for the relative population of states is as given as 2J into J plus 1 exponential E minus EJ over KT. So if we look at a sample data, we notice that these are the population as given by Boltzmann. So we notice that as J increases, 0, 1, 2, 3, 4, the degeneracy increases, which means as there are more states available there are more energy levels available in the upper level. In the ground states, there is only one level. Then the first excited state with J equals 1, you have 3 possible energy states with the same energy. However, the exponential factor decreases from 1.0 to 0.89. It decreases with J. So the degeneracy increases, the exponential factor decreases. This definitely leads to a distribution that we are usually familiar with. So there is an increase. If you look at N over N naught, so we have an increase. It gets to a certain maximum. So from 1.0 to 0.9, 4.7, all the way to 9.0. And then it starts to decrease, 8.8, 8.3, 7.6, and it goes on and on. So here we went from 0 to J equals to 0 to J equals to 50. So there's a distribution of population. So it reaches a maximum, there's a value. So in this, J equals to 7 for this one here. In this diagram, J is about 12. So it's important to note that it is not always 7 or 12. It depends on the molecule on the temperature as well. So the population shows a maximum at a value that corresponds to the differential of when this differential with respect to of this equation is equal to 0. So that's the tangent of that place at this. So because this is relative population plotted against J, so the tangent here corresponds to this differential being equal to 0, and this is obtained to be J max equal KT over 2 HB minus half. So this is when B is given in joules, and we have, if our B is given in wave numbers, we have that equation. So like we said, it depends on the temperature. At 50 degrees, these are our J levels. 50 degrees Kelvin, these are our J levels. Say J1 is very populated. If you increase the temperature to 200 Kelvin, J4 is very populated. At 302 Kelvin, you see, the population keeps increasing and the distribution curve changes as the temperature increases. Our B is kept constant. This is for the same molecule. So this also buttresses the point earlier mentioned in a previous video that rotational energy levels are close apart and are easily populated, unlike vibrational energy levels and electronic energy levels that require much energy to excite them. Now, why is this important? It's often used to calculate temperatures in different zones. So we take an example. The average spacing between the average spacing between successive rotational lines of carbon monoxide, that's what we worked on previously, is 3.86 wave numbers. Determine the transition that gives the most intense line at 300 Kelvin. So we have our J max to be equal to this. So we're going to use this equation because our B is given 3.826 per centimeter. So what is B? B is 1.913. That's 3.826. So why did we divide it by 2? Because it says the average spacing, and if you recall, the average spacing is 2b. That's 2 multiplied by b, so we can obtain our b. So using this equation, our J max is given as K, that's the Boltzmann constant, multiplied by the temperature 300 Kelvin, divided by 2 times Planck's constant times the speed of light. Note that this is times 10 to the 10 but centimeters per second, times the rotational constants that we just obtained, everything square root, minus 1 over 2. Approximately this comes to about 6.88, which is around 7. So the transition with the max will go from the state 7 to state 8.